Section 14.4 Diffie Hellman key exchange. So much for classical methods. Let's talk about a more modern method. Diffie Hellman key exchange was invented in 1976 by Martin Hellman, a professor at Stanford University, and Bailey Whitfield Diffie, his research assistant, later of Sun Microsystems. The underlying concept of public key cryptography was invented in 1974 by Ralph Merkle, then an undergrad at UC Berkeley. The essential feature of Diffie Hellman key exchange is that Sandra and Riva can establish a secure encryption key even if Emily intercepts all of the messages they exchange. To set up the exchange, Sandra and Riva must agree on a large prime, P, and a primitive root, W, of that prime. Or Sandra can simply choose P and W and send them to Riva. P and W can be sent in clear. Recall from section 13.3 that it is easy to find primitive roots. For most primes, at least one of 2, 3, 5 or 7 is a primitive root. Sandra chooses a secret exponent S and computes x equals w to the power of s mod p. She sends the value x to Riva, but keeps the value of s to herself. Riva chooses a secret exponent r and computes y equals w to the power of r mod p. She sends the value y to Sandra, but keeps the value of r to herself. Now Sandra can compute y to the power of s mod p, which is w to the power rs mod p, and Riva can compute x to the power of r mod p, which is w to the power sr mod p. Since w to the power rs equals w to the power sr, Sandra and Riva have computed the same value, which they can use as an encryption key, or which they can split into several encryption keys. An efficient way of performing the exponentiations is described in section 13.3. Some authors, and Wikipedia, describe Diffie Hellman key exchange as a public key method. They talk about combining Sandra's and Riva's public keys and their private keys. This is not true. There are no public keys involved in Diffie Hellman. Even if you consider the exponents r and s to be keys, they are both secret keys. Suppose Emily has intercepted all of the messages between Sandra and Riva. Then Emily knows P, W, X and Y, that is, W to the power S mod P and W to the power R mod P, but she does not know S, R or W to the power RS mod P. Determining W to the power RS mod P is called the Diffie Hellman problem. It is not known if this is the same as determining R and S, but they are believed to be equally difficult problems. Determining S and R, given P, W and either X or Y, is known as the discrete logarithm problem. It is known to be a very difficult problem. When P, R and S are sufficiently large, the problem is believed to be computationally infeasible. Experts disagree on how large P must be, but common recommendations are 300 and 600 decimal digits. Some implementations allow for P to be up to 1234 decimal digits, which is 4096 bits. The exponents r and s can be much smaller. Expert recommendations range from 40 decimal digits up to 150 decimal digits. An algorithm called the Silver-Pohlig-Hellman algorithm, for Roland Silver, Stephen Pohlig and Martin Hellman, makes it easy to solve the discrete logarithm problem when p-1 has only small factors. The algorithm lets you solve for each of the small factors separately. Therefore, Sandra must make certain that P is a safe prime, meaning that p-1 has at least one large factor, say q greater than 10 to the power of 35. Ideally, Sandra would choose P to be a prime of the form 2q plus 1, where q is also a prime. The corresponding prime q is called a Sophie-Germain prime, named for French number theorist Marie-Sophie Germain, who also studied acoustics and elasticity. It is even stronger if q-1 and q plus 1 both have large prime factors. In the next section, we will explicitly construct q so that q-1 has a large prime factor. It is highly likely that q plus 1 also has a large prime factor, simply by chance, just because q is so large. Numbers that have only small factors are called smooth numbers. They become very rare as the numbers get large. Section 14.4.1. Constructing large primes, old. The conventional method for constructing large primes, which you can find on many websites, begins by randomly choosing an odd number n of the desired size, and then testing whether n is prime. First, you try a few hundred small primes. If n is divisible by any of these, then it's not prime. Choose again. This preliminary test is worthwhile because it is so fast. Next, you test whether n is prime by applying a probabilistic primality test. The most common test is the Miller-Rabin test, invented by Gary L. Miller and Michael O. Rabin. Let n-1 equal 2 to the power h d, where d is odd. That is, 2 to the power h is the largest power of 2 that evenly divides n-1. The first step is to choose a base b in the range 2 to n-2, and test whether b to the power d is congruent to 1 mod n. If this is true, then n passes. If not, then see whether b to the power 2d is congruent to -1 mod n, or b to the power 4d is congruent to -1 mod n, etc. Keep going as long as the exponent 2 to the power g d remains less than 2 to the power h d. If you find such a value g, then n passes the test, and b is called a witness for the primality of n. If no such g is found, then you know for certain that n is not prime, so you must start again with a new value for n. If n passes, there is still a 1/4 probability that n is composite. If you want to push the probability that n is not prime down to 1 in 2 to the power 128, you will need 64 Miller-Rabin tests, each with a different base b. Unfortunately, this is still no guarantee. The Miller-Rabin test falsely identifies the Carmichael numbers as prime. These are numbers that are not prime, but for which every b is a witness. They were discovered by Robert Carmichael of the University of Illinois in 1910. The first few Carmichael numbers are 561, 1105, 1729, 2465, 2821, 6601, 8911, 10,585, 15,841, 29,341, and 41,041. Carmichael numbers tend to have small prime divisors, so passing 64 Miller-Rabin tests and also finding that n is not divisible by any of the first few hundred primes makes it overwhelmingly probable that n is a prime. This is a good method for finding primes of a particular size, but it does not guarantee that n is a safe prime, and it is much slower than the method of this section. If S is the size of the primes you need, the number of trials you need to find a prime is about ln of S. So, for a 500-digit prime, you need about ln of 10 to the power 500, or about 1,151 trials, each requiring 64 Miller-Rabin tests and hundreds of trial divisions. Using the method I present in this section, can save you hours or even weeks of computer time, depending on what kind of computer you are using and how large the primes need to be.